Today's lesson will be an introduction to differential equations.
In this classical mechanics course, we'd like to describe the motion of objects. For example, the motion of a projectile flying through the air. Or maybe the back and forth motion of an oscillator. Or perhaps something more complicated. For example, these disks in angular motion. To solve these problems, we need to talk about rates, that is, derivatives. This is because in order to solve for the motion of the objects, we need to consider methods to solve Newton's second law.
Newton's second law says that the force on an object is equal to its mass times its acceleration. This is actually a differential equation. To see this, let's rewrite it in terms of the displacement r. We call this differential equation an ordinary differential equation. If it contained partial derivatives, then it would be a partial differential equation. This is also a second-order differential equation because it contains the second derivative of r. If instead we rewrote this equation as force equals mass times the derivative of velocity, then this would be a first-order differential equation because it contains the first derivative with respect to velocity. It's a lot easier to solve a first-order differential equation than a second-order differential equation. So this rewrite, while trivial, is actually really important. In today's lesson, we're going to be learning all about different types of differential equations and how to solve them.
Let's learn more about these rate equations and take a formal look at the mathematical field of differential equations. Our text of reference will be Boas's third edition of Mathematical Methods in Physical Sciences, Chapter 8, Sections 1 through 3.
Our learning goals for this lesson will be to 1. Identify different types of differential equations. 2. Develop techniques to solve differential equations such as separate and integrate, integration factors, and guess and check. Let's learn more about these rate equations and take a formal look at the mathematical field of differential equations. Our text of reference will be Mathematical Methods in the Physical Sciences by Mary Boas. We'll be looking at Chapter 8, Sections 1 through 3, and you should read these and follow along with the lesson. Our first learning goal is to identify the types of differential equations. First, let's identify some differential equations and talk about them using the nomenclature in the field. We've already learned that the order of a differential equation is the order of the highest derivative in the equation. These two equations both have the second derivative, so these two equations are second order. These two equations both have first derivatives, so these equations are first order. We also know that all of these equations are ordinary. That is, they don't have any partial derivatives. The r, the I, the v, and the q are only functions of t. In addition, all of these differential equations are also linear. A linear differential equation is one that has the form a0y plus a1 dy dt plus a2 d squared y dt squared plus on and on equals b, where a0, a1, a2, and b are all constants or functions of the independent variable t. Here I've labeled the dependent variable as y. Now you're going to have to be careful about which ones are the dependent variable and which ones are the independent variable. You'll know by the derivative, but I'm just going to call the dependent variable y in this case, but it might be x or q or r in a bunch of other cases. The independent variable I'm going to call t, but it could be x or y or anything. So you're just going to have to look at the derivative to make sure that you understand which one is the independent variable and which one is the dependent variable. Okay, so our differential equations are going to be of this linear form. And actually there's two types. We could either have an inhomogeneous linear equation if the b is some function of t or a constant, or we could have a homogeneous linear equation if the b is equal to 0.
During this semester, we'll be solving both homogeneous and inhomogeneous linear differential equations that will require different techniques to solve them. In order to do so, it will be important to identify which type of differential equation we have so that we know which technique to use. Let's do some practice problems.
In our first problem, I want you to find the following differential equations that are not linear differential equations. If you look through these differential equations, you'll find two that are not linear differential equations. Let's just look at each to make sure you understand what's happening. Here we've got dy dx. Y here is the dependent variable and x is the independent variable, cosine x. So this is fine, it's still linear because this is a function of the independent variable. However, dy dx equals sine y, now this is a function of the dependent variable, and remember our dependent variable can only have y's or derivatives of y. So this one is not going to be linear. This one here is linear, as is this one, since all of our constants here are functions of the independent variable. However, this equation here has the dependent variable squared, and so this is not going to be linear. Again, this one will be linear, as will this one. Let's do another problem. I want you to find the following differential equations that are homogeneous, and I want you to give the order of the differential equation. The ones that are homogeneous are actually these two. This one has a function of the independent variable, so this one has a b of cosine x. This one also has a function of the independent variable, so this one has a b of a sine omega t. However, this one, usually we write this on the other side. This is the dependent variable, but there doesn't seem to be any functions of the independent variable or constants. So this one is homogeneous. Likewise, this one is homogeneous. And this one is not homogeneous because you've got these functions here of the independent variable. If we go through and list the order of the differential equations, here we've got a first order, because we've got the first derivative, second derivative, so second order, second derivative, second order, second derivative, second order, and first derivative, first order.
If you had trouble with these problems, you can get more practice by looking at the problems in Section 1 of Chapter 8 in BOAS. If you are able to identify all of these differential equations, then great job! This means that you're familiar with the naming conventions and are ready to talk about techniques for finding solutions to these differential equations.
Our second goal will be to develop techniques to solve differential equations. Here we will be learning about the technique separate and integrate.
Here we want to learn some techniques for finding a solution to a differential equation. We will define a solution to a differential equation as a mathematical relationship between the dependent and independent variables that would yield an identity if we substituted it back into the differential equation. We can use any technique that we want to find this relationship. As long as the relationship makes both sides of the differential equation equivalent, then we know that the relationship is a solution. The first technique that we will discuss is the technique that I'll call separate and integrate. You're probably familiar with this technique without even knowing it.
Let's suppose that you have the differential equation dy dx equals f of x, and you want to solve this equation. The first thing that you would do would be to separate the independent and dependent variables. You would do this by writing dy equals f of x dx. This is the separate step. Then you would integrate both sides. This is the integrate step. This integration would give you your final answer. This integral, of course, also gives you the solution to the original differential equation. Many first-order linear differential equations can be solved just by using the separate and integrate technique. You've probably done this before, but let's do some practice problems to get the hang of it. In the first problem, you're given a differential equation, and I'd like you to solve for v using separate and integrate. To solve for v, we first eliminated the variable m. We've separated the independent and dependent variables onto either sides of the equal sign. And then we've integrated. Again, remember that we've got a constant of integration here that you should definitely make sure that you add to your equation. Let's do another problem. Given this differential equation, solve for v. To solve for v, we're first going to separate the dependent variable v from the independent variable t. Then we'll integrate both sides. Finally, we can solve for v. Make sure that you don't forget this constant when you integrate the indefinite integral. This constant is extremely important.
You see, these constants are important because both of the solutions that we have just found have been general solutions. That is, they are general in that they represent a family of curves that are solutions to the differential equation. This is because all of the constants are undefined. For linear differential equations of order n, the general solution will contain n independent arbitrary constants. For example, a second-order linear differential equation should contain 2 independent arbitrary constants. Here in this example, the order of the differential equation is first order. So each of these examples only contains one constant. By changing the value of this constant, we can find all of the solutions to the differential equation. However, usually we just want to find the particular solution, or the solution that satisfies the differential equation, and some other requirements as well. One of these requirements is that the constants are defined such that they allow the boundary conditions to be satisfied.
After we find our general solutions to our differential equations, we're going to need to find the particular solution. To find a particular solution for both of our examples, we need a boundary condition. Let's say that for both of our examples, the ball initially starts out with a velocity of v0 when t equals 0. If we plug this back into our answer, we can find that our constant is now v0. This gives us a solution of v equals gt plus v0 for our first problem. This is called the particular solution. Remember, the general solution is where this v0 is just a constant, and it represents a family of curves. The particular solution is the particular curve that solves our differential equation and the boundary conditions. For the second problem, we'll do something similar. We start off with this differential equation, and we found that the solution was constant e to the negative bmt. We're again going to insert our boundary condition that when t equals 0, v equals v0, and solve for the constant. This gives us a particular solution of v equals v0 e to the negative bt over m. Let's try solving one more example problem using the technique of separate and integrate, and this time we'll just go right ahead and find the particular solution to the differential equation. In this problem, I want you to solve for y, and the boundary condition will be that y equals 1 when x equals 0. To find the solution, we first need to separate the y and the x. What we'll do is we'll factor out the x, and then we'll divide by y plus 1, and move dx to the other side. After separating the variables, we'll integrate both sides. This will give us the following equation. Don't forget the constant from the indefinite integral. If we take the exponential of both sides, we find that y equals constant e to the x squared over 2 minus 1. We can now use the boundary condition to get our particular solution. Inserting the boundary condition, you should find that y equals 2e to the x squared divided by 2 minus 1.
Hopefully you were able to easily find the solutions to these example differential equations by using the technique of separate and integrate. If not, you can complete some more practice problems in Chapter 8, Section 2 of BOAS. The problem with the separate and integrate technique is that it's not very general. Let's discuss a general method of solving first-order linear differential equations.
Our general method of solving first-order linear differential equations will be to use an integration factor. Let's say that we want to solve a first-order linear differential equation with the form dy dt plus ay equals b, where a and b are constants or functions of t. This equation in general is not separable, But if we multiply it by an integration factor, then we will be able to separate and integrate it. It turns out that the appropriate integration factor is e to the integral a dt, or what we'll call e to the I. I won't tell you how we actually derive this integration factor. I'll just show you that it works. First, we're going to multiply both sides of our differential equation by the integration factor. Interestingly, this left side of the equation is actually equal to the derivative of y times our integration factor. If we then go ahead and substitute this back into our original differential equation, we get the following equation. It turns out that this is separable because this term, b e to the I, is a function of t only, and thus we can separate it. Separation looks something like this, and then we'll go ahead and integrate both sides. We end up with the following answer. Here c is now our constant of integration, which is the one arbitrary independent constant needed for the general solution to a first-order differential equation. Finally, we can solve for y. Y is just going to be this equation, which is slightly messy, but will always give you a solution. Before we go ahead and solve some first-order linear differential equations, let's notice something that's kind of cool. The second term in this general solution, this c e to the negative I, is the solution to the homogeneous version of the differential equation. That is, this is a solution when b equals 0. This is easy to see as the first term disappears when b equals 0. Because the second term and its derivatives will all vanish when we substitute them back in, that means that the first term in the general solution will solve the differential equation exactly, without any need for the first term. We call this the particular solution. I've labeled it here y particular. This one, which solves the homogeneous version of the equation, is called the complementary solution. It turns out that the general solution to any inhomogeneous differential equation will contain both the particular solution and the complementary solution. So of course, the expression that we have found for the general solution to a first-order linear differential equation follows this pattern. Let's go ahead and use what we've learned to solve a first-order linear differential equation via an integration factor. Why don't you go ahead and solve the following differential equation for v using our technique of integration factors. This differential equation might be familiar because it describes a ball of mass falling vertically downward due to gravity. The gravitational constant here is g, the mass of the ball is m, and it turns out that this drag coefficient on the ball is b. Go ahead and solve for v using the expression for the general solution we just found. First, let's solve for the integration factor ei. If we plug in our constant here, we find that e to the integral of bt dt over m is just going to be e to the bt over m. That's our integration factor. We'll plug that in for the formula for v, and we get the following solution. Integrating gives us v equals mg over b plus a constant times e to the negative bt over m. Here the particular solution is mg over b, and our solution that solves the homogeneous equation, the complementary solution, is this second term. You should verify that this solution solves our differential equation. If you'd like more practice with solving differential equations using an integration factor, look in Chapter 8, Section 3 of BOAS.
With this tool in hand, we can now solve any first-order linear differential equation. But what about other types of differential equations? Let's discuss a more general method of solving differential equations, which is guess and check.
In this section, we'll talk about solving differential equations using guess and check.
In the guess and check method, one guesses the form of the solution should take, and then checks to see if the solution is correct. While this technique is not very powerful, it allows us to discuss solutions to a whole host of differential equations. Let's try this technique out.
Let's do the problem where we're given the following differential equation and we want to guess the form of the solution for x. So we've got the second derivative of x is equal to negative omega squared x, where omega is a constant. See if you can just guess the form of the solution for x. To try out the guess and check technique, let's do a problem. The problem is that given the following differential equation, I want you to guess the form of the solution for x. Just looking at this differential equation, you might guess that the correct solution would have a second derivative that's the negative of itself, because this omega here is just a constant. In other words, the correct solution would have to be cyclic. Now, what functions have cyclic derivatives that you might guess would be solutions to this problem? Go ahead and tell me what functions are cyclic. You might have guessed an exponential, or perhaps a sine or a cosine. Maybe some of you even thought of a hyperbolic sign. Actually, all of these could be fashioned into a general solution. Let's just pick one of them. How about a cosine function? Here we have two arbitrary independent constants, a and delta, and we've got our omega, which is the constant from our differential equation. Remember that we have to have two arbitrary independent constants since the differential equation is second order. Now let's check to see if this solution works. First, let's find the first and second derivatives. And then we'll go ahead and we'll plug these back into our original differential equation. We come up with the left side equaling the right side, so we know that this solution works. Now what if we had tried another guess? Let's say that we had tried a cosine omega t plus b sine omega t. we have a and b as our two arbitrary independent constants. Does the general solution of this form work? To check the solution, we'll first find the first and second derivatives, and then we'll plug them back into our original equation. If we do this, we see that our x times a negative omega squared is equal to our second derivative, so we know that it works. But some of you might be thinking, well, hey, wait! What is going on? Are there two solutions to this one differential equation? Well, it turns out that actually this solution is completely equivalent to the last solution. So no, there's only one solution. But what if we had picked a different solution, one that was not equivalent? Let's say instead that we picked a cosine omega t. That's not equivalent to a cosine omega t plus b sine omega t. Does this solution work? Go ahead and try it out. It turns out that this solution, a cosine omega t, doesn't work because you need two arbitrary constants, and this one only has one. Sure, if you put it back into this differential equation, it seems to work, but you won't be able to solve the boundary conditions with only one arbitrary constant. You need two. So there's a subtle reason why this solution does not work.
Hopefully you've seen that the guess and check method is certainly general, but that sometimes it's hard to find the right guess. If you dig deeper into the field of differential equations, you'll find many more sophisticated methods for solving differential equations involving substitutions, linear algebra, Laplace transforms, Fourier transforms. For more information on these methods, you can read further into Chapter 8 of Boas.
The learning goals for this introductory lesson to differential equations are first to identify the different types of differential equations, and second to develop techniques to solve those differential equations such as separate and integrate, integration factors, and guess and check. By the end of this lesson, you should be familiar with these two learning goals.
The techniques that you develop now will ultimately be useful in solving problems using Newton's second law, allowing you to, for example, characterize the actual motion of a projectile as it moves through the air. That's it.